In this session, we're going to look at how to implement the Beer-Lambert law using GPU. So we saw previously that we need to compute the Beer-Lambert law, and really what is probably the most difficult part is to know the thickness that a photon has crossed through an object. And to do that, we're going to use polygon meshes as made of triangles. And we need to know for each ray from the source to the detector, what are the intersection between that ray and the object. Now we don't know the order of intersection because that will depend on, well, which triangle has been found first. So we will need to sort this intersection, and that can possibly be done using GPUs. And the technique is called depth filling. But this is not really what we will want to do. This is a bit time consuming, and this is actually not needed. So there is this notion of L buffer from Freud. And if we use a convention in graphics, in CG, normal vectors are outward. So they point to the outside of the mesh. And you can see this. So if we use the dot product between the view vector and the normal vector, and the sign of that dot product, well, we could probably sort it out. All these vectors are known. The only thing we need to do is to solve this equation. So I will refer to the ith intersection in any order. Di is the distance from the X-ray source to the intersection point, which is known as well. This is the sign of the dot product between the view vector and the normal vector. And that can be computed using a shader program. This is also, something that we can get in the shader program. And this is the value that we will give to the fragment, to the pixel. And for X pixel, we will do that. And thanks to high dynamic range rendering in OpenGL and the blending function, we can sort out this sigma sign here. So we had to modify the graphics pipeline. And this is something we can do now with OpenGL. So we use 3 frame buffer objects with high dynamic range so that we can do some offline rendering. And for each object of the thing, we're going to compute the L buffer. And we need to integrate that. So here I show in green the elements of the graphics pipeline. So here we're going to integrate the energy. In red, well, we're going to integrate mu time LP. Here. And in blue, we're going to compute the L buffer for each object. And you can see the different for loops. So we do that for every object. And we integrate in that frame buffer. And we also integrate for all the simulated images. So yeah, if you have an interactive pipeline. So if it was not interactive, we could get rid of that for loop here. As you know, we have polychromatism, and this is known as beam hardening. And in that case, we need to iterate through all the energies that are in the beam. So here's an example. So again, a cube with a cylinder, and here is the beam that we can use. Here is the average energy in that beam. Here is the peak energy. So here I tried 3 different cases, 2 monochromatic, one polychromatic. So a monochromatic at the average energy, at the maximum energy, and the polychromatic beam. And you can see the differences in the profile. So when we simulate the 3 X-ray images, we look at the pixel values along this line and we plot it here. And you can see that this is actually not the same. So this is something that could matter depending on your needs. We could also simulate different source shapes. Parallel beam, let's say the source is very far away from the detector, we could do that. Infinitely small point source, or a source that is cubic, it could actually be of any shape, so that we can simulate the focal spot of X-ray tube. And in that case, if we have all the parameters, we have to integrate through the energies and through the virtual points here. So another loop. So more loops here. And we have a much more complex graphics pipeline in that case. We needed to add four loops. So for the A is just to clean up data. We have to iterate through all the point sources and through all the energy channels, and finally integrate the final image. And if you're interested in how it's been implemented, so further details will be in these 4 different papers. So here's the first paper, and we added more complexity. So what we're going to do next is to look at, well, once it's been implemented, we have to make sure that it works. So the validation is the next topic. To make sure that the X-ray images that we compute are accurate.